Hello guys, welcome back to CFD College. I'm Ashkan and this is another tutorial on ANSYS Fluent. This is the second part of a full tutorial on flow simulation of the flow over a cylinder. Uh, if you remember, in previous video, we created the domain, two-dimensional domain, and we generated a structured mesh for this flow. And in this video, we are going to perform the simulation in ANSYS Fluent and post-process the results. So before starting the video, if you haven't subscribed to the channel, please do it. In this channel, I usually present two or one videos every week. The videos, are mainly about CFD, ANSYS Fluent, pre-processing, post-processing, and something related to numerical simulation uh, of different projects. And if you like these videos, if you find these videos useful, please share them with your friends. Please introduce us to your friends. Okay, now let's jump to the video. We would like to simulate uh, this phase B, in which we have a symmetric pair of symmetric vortices. The Reynolds number should be between 5 and 40. If you remember, the diameter of the cylinder is 1 meter. The working fluid is air with density of 1.225 and viscosity of 1.8, 10 to negative 5. So let me open an Excel. So we have density, viscosity, diameter, and velocity of the flow. Density is 1.225, viscosity 1.8 E minus 5, diameter is 1 meter, and we have Reynolds number. I pick 20, so the Reynolds number equals 20, and now I can find velocity. Reynolds number times viscosity divided by density and diameter. So velocity is 2.94 E minus 4. If you want to have a Reynolds number of 20, this should be the velocity. So this is workbench. If you double click on the setup, you can see Fluent Launcher. Okay, I think it's fine for me. I always use double precision, so I always check that. And for these simulations, I use I don't use parallel mode. I think this simulation doesn't need that to use multiple CPUs in parallel mode. Just wait for the Fluent now. Okay. Flow is steady because we have stationary vortices. It's 2D, pressure-based. Flow is laminar. Material is air. You can see the density, and I should modify viscosity. Let's go to boundary conditions. Inlet. The velocity is 2.94 e minus 4. 2.94 e minus 4. As you can see, the domain can be larger, especially the distance between the cylinder and the upper and lower sides. Okay, that's good. Cylinder is wall, outlet is pressure outlet with atmospheric pressure. Gauge pressure is 0. If in operating conditions, if you check there, you will see operating pressure, which is 1 atmosphere, 101, 325, 1 atmosphere. And the sides can be symmetry, or if they are wall, you can modify shear condition from no slip to shear to a specified shear of 0, meaning that these sides, upper and lower walls, are shear free. So we don't have no slip boundary condition. And that's it. There is no need to modify mesh interfaces, dynamic mesh. But about reference values, select inlet for compute from. This way, the velocity is automatically updated, and also the density and viscosity. But about length, depth, and area, the length is the diameter of the cylinder, which is 1. Depth is 1 meter. So 1 multiplied by 1 equals 1. And that's it. Yeah. Methods. If you go to method, coupled is good. The scheme of coupled for pressure velocity coupling is fine. Maybe you can change it to simple if your system is not, is not good. It's a bit old and it's not powerful. Pressure discretization is second order, and the momentum is, and for the momentum is second order upward. I think it's a good idea to monitor the drag coefficient and drag force. So right click on report definitions, new, force report, drag. CD of the cylinder. Here you can choose whether you want drag coefficient or drag force. In this study, I will go for drag coefficient. What else? You should select appropriate zone, appropriate boundary, which is cylinder in this problem. If you want to see the value in the console, check this option, print to console. And if you want to see the plot and or have the file after the simulation, for example, you can copy it to Excel and see the trend of the plot. Make sure that these two options are selected. And for the drag coefficient, the vector is fine. X is 1 and Y is 0. Okay, monitors. For now, I deselect check convergence for all the equations. And now I think it's time to initialize the project. So I use hybrid initialization, and you see it's done quickly because the number of cells is not too high. It's 24,000. It's good. And since it's steady simulation, we don't need to specify autosave for data file because we only need the final data, final results. And I think 500 iterations can be enough. And let's let's just start with 200 and see the residuals, the trend of the drag coefficient, and then we can decide whether it needs more iterations or not. Okay, just click on calculate. Here you can see uh, the percentage of iterations that are done. You can see here 50, 40 iterations remaining. And here in the console, you can see the residuals. As you can see here in this chart, 200 iterations is more than enough. So the residuals is fallen to up to 10 to minus 12. You can see here and here. And for the continuity equation, the velocity, x and y momentum is even smaller. That's super great. And here, the fourth, 1, 2, 3, 4, 5, fifth color shows us the drag coefficient. As you can see, after around uh, 30 iterations, uh, it's constant, yes. So if the only thing that matters for you is the drag coefficient, 30 iterations are enough for you for this particular project. And even if we uh, didn't deselect the, if we haven't deselected the convergency, check for continuity and momentum equations. And I think, yes, it's around 30, 33. The simulation would stop after 32 iterations, but it's better to see this kind of residual plot. Residuals are fallen and then they become straight lines. It's important in CFD for residuals to become straight lines in steady and also in transient simulation. But in transient simulation, this should be done in every time step, not in transient simulation. You will see in this tutorial, it's a bit different. And in each time step, we need to have something like this. It doesn't need to be, these lines, the residuals, don't need to become straight lines, but they have to, you have to see this trend, start from point here above, here high, and then decreasing. So the residuals should be decreasing in both steady state and transient simulation. But in steady state, the final results is better to see. It's better to see the residuals are straight lines. But actually, it depends on the threshold. For example, if you define the residuals threshold, for example, 10 to minus 6. So here, somewhere here, simulation will stop, and that's fine for you because the residuals have reached the value that you wanted. So, but if the value of residuals are not sufficiently small, then you have to check whether uh, whether they have become straight or no. For example, the worst case scenario is when you see residuals are fluctuating and the fluctuations are not small. I think you will master these concepts in future videos. So now this is uh, the monitor. As you can see, the drag coefficient started from, whoa, really high value. It's around 55, and then it decreased to this value, 2.42 for the cylinder. Okay, now post-processing the results. If you want to learn CFD post or tech plot, I have two playlists, many tutorials about CFD post and tutorial and tech plot. You can watch them. But here in ANSYS Fluent, if you go to graphics and contours section, you can see, for example, pressure. And remember that in 2D simulation, you don't need to select any surfaces for uh, contour, for creating contours. So this is static pressure. And let's look at velocity. This is the velocity. You can see the wake here, and it has reached to the outlet. That's why we want to extend the domain from all sides, the front, the back, and the sides of the cylinder. And what else? We can see the velocity vectors. See these are the vectors here. Since the velocity is not high, you can't see the vectors, but we can change the style to arrow, which is 2D, the display for the display in 2D, two-dimensional. And then we can increase the scale, for example, to 5. Now you can see here we have these vortices. We have two vortices here, and here is the wake. You can increase the skip if you want to see fewer vectors. But maybe the best way to see the vortices is using path lines. Path lines should be the path line in ANSYS Fluent is streamline. So path line is streamline. If you want to see the streamlines, you can use the path line option that is available in ANSYS Fluent. Okay, now here you can see the streamline, which are colored by particle ID. You can change it to velocity. It's better. And if you pay attention, there is no streamline here because here we have two vortices. So what should we do? We should create a line. So if here is the origin the diameter, the radius of the cylinder is 0.5, so that's x equal to 1, and from minus y from -1 to 1 create. Now click on display to see the line. Where is the line? Notes. Okay, leave it. Let me. X is 1 and minus. Okay, I think it should be okay. So let me add line 1. Oh no, here. It's okay. Oh, now I realize that the color of the line is white. That's why we can't see it, because of the color. Uh, okay, but if you see, we have uh, streamlines in the wakes region now, and you can see the vortices. And click, if you select draw mesh, you can just select the cylinder, check it, then close it, and then display. Now you can see the cylinder, and you can modify the line. For example, you can reduce the x coordinate of the line, but I think it's fine. Now you have streamline, velocity streamlines everywhere, and you can see we have a pair of symmetric vortices behind the cylinder. It's perfect, I think. And what else? That's it, I think. Uh, it's a good practice for you. If you are a beginner, please watch all these videos step by step from now on. This is the second video. Don't forget that. We have another video, the first part of this tutorial. And I think it's enough for this video. After in the next video, let's simulate phase C, where we have vortex straight, von-karman vortex shedding, von-karman straight. The Reynolds number should be between 40 and 200, and that simulation should be done in transient mode. So thank you for watching this video. Please subscribe the channel if you haven't done that, and give us a thumbs up button. Share these videos with your friends, and I hope you've enjoyed not only this tutorial but also the other videos that I have. So again, thank you for watching this video. Until the next video, take care of yourselves and bye bye.